The disjunction of P and Q is denoted with a right side up V, and this is really the statement P or Q. This statement is an inclusive OR, meaning that by virtue of the English language, the outcome P or Q is true whenever either statements or both statements are true. So in our truth table, we wrote false, true, to look at all the combinations of how P and Q could be paired together. Well, if both of the input statements are false, then it is not true that one or the other, right? So in other words, if I said, I will clean my room or I will go to the store, if I did none of those things, then you'd call me out as a liar. But if I said, I will clean my room and I will go, or I will go to the store, and I only go to the store, but I don't clean my room, that's a true statement because I use the word or. And same thing here. If I did go to the store, but I did clean my room, but I didn't go to the store, and I use the word or between those, then that would be a true statement. And also, this is an inclusive or statement, meaning that if I've done both of those things, that you would still call me a truth teller. So it's kind of like an and statement. It's true when both are true, but it's also true when just one or the other is true. Let's try that again. So that's an inclusive OR. Usually we don't talk a lot about exclusive ORs unless the context just naturally dictates that it only makes sense for it to be an exclusive OR. Okay, under what conditions can a student take a class that has the following requirement? Students who have taken calculus or computer science can take this class. So that would mean that I've taken, the first situation would be calc, but not computer science. So maybe I took calculus, but I did not take computer science. Because this is a disjunction, as long as I've done at least one of these two things. So another way to say this is at least one of PQ. Another way I could have satisfied these requirements is if I've taken computer science, but not calc. And they certainly won't say, well, you've taken both, so you can't take the class. If I've taken both of those, I've definitely satisfied the requirements as well. So under any of these three circumstances, I can take the class that this is a prerequisite for. Now, there is a definition for the exclusive OR of P and Q, denoted P with a plus sign circled, is a statement that is true when exactly one of the statements is true. Exactly one, meaning if it's an exclusive OR, so it can't be both. So for example, a situation where you might see this is, let's say you tell a child, you can have chocolate. That's not what I want. We can say you can have chocolate or a bowl of ice cream. Well, if we're telling this to a child, usually we mean this as an exclusive OR, right? If they say, well, I'll take both, because by definition, OR means one, the other, both. But really, the way the parent meant this is to say, you can have one, the other, but not both. And so you can see in this table that the only outcome for true is when just one or the other is true. But if both of them are if both of those statements are true, the exclusive OR is a false statement. So if the child said, I want both, the parent would say, no way, you're not getting it. Okay, so but now we often want to combine these. So we have conjunction, disjunction. Those are the most common ones when we're dealing with ands and ors. We also have something called a conditional statement. Conditional statement is one of the form P, and then there's an arrow pointing to Q, and this reads, if P, then Q. So this is kind of like an if statement when you're dealing with computer programming. The statement must be true whenever the condition P happens and the conclusion follows. So whenever P happens, we're saying then Q. Q is guaranteed to happen after that. It is much like an if-then statement in programming. However, the only time this type of propositional statement is false is when the condition happens, but the conclusion does not follow. So, for example, before we start to look at the truth table of this, let's consider the following statement. If I am elected, then I will lower taxes. So if we reason through this and we say, what is this politician really saying? The politician is telling us that if he or she is elected, voters would expect this politician to lower taxes, right? So suppose the person is elected, they lower taxes, they've told the truth. Furthermore, if the politician is not elected, then voters will not have any expectation that this person will lower taxes, although the person may still have sufficient influence to cause those in power to lower taxes. So if we think about this statement right here as P, and we think about this as Q, and we look at when we would expect this to be, this P implies Q to be, or if P then Q to be true. So if the condition happens, he's elected, and he does lower taxes, then he has told the truth. But if he is not reelected, he still lowers the taxes. The statement itself is still a true statement. It doesn't say, I will only lower taxes if I am elected. It just says, okay, I promise you that if you elect me, I will lower taxes. But there's nothing stopping that person from lowering taxes anyway. And now if, let's say, the politician isn't elected and he doesn't lower taxes, he still told the truth because he didn't guarantee he would lower taxes. He didn't say anything about lowering taxes if he wasn't elected. But so we just say that statement is true. So the only time it's false is if, let's say, he is reelected, or he is elected, but he doesn't lower taxes, he has told a bold-faced lie. And in that case, we would say that's the only circumstance in which an if-then statement is false. So here's the truth table for it. So it is only when the politician is elected but does not lower taxes that voters can say that the politician has broken the campaign pledge. This last scenario corresponds to the case when P is true but Q is false in the if P then Q statement. So here's the truth table for it. So we can see that it's always true. The only time it's false is whenever P happens, the condition happens, but the conclusion doesn't happen, then that if-then statement is not working properly. It's a false statement. Now, there are lots of ways in if P then Q can show up. So the most common is the first one here. You can see if P then Q. Some people will, so I'll just kind of highlight the most common ones that you'll see. If P then Q. P implies Q. So that's the same thing. If P comma Q, P is sufficient for Q. Okay, so P is sufficient for Q means that the way you can think about this is that if P happens, that is sufficient enough for Q to happen. Another way you could say that same thing is a sufficient condition for Q is P. So the condition P happening is sufficient for Q to take place. Q if P, that's just the same thing, just saying if P then Q. Q whenever P. Q when P. Q is necessary for P. That's kind of a weirder one, but it means it's necessary. It necessarily happens when P takes place. A necessary condition for P is Q. So if P does happen, Q happens. Q follows from P. Q unless P doesn't happen. So some of these are less common ones, but just so that you're aware of other statements, you can always reference this. Example 3, let P be the statement Maria learns discrete mathematics, and Q the statement Maria will find a good job. Express the statement P implies Q as a statement in English, then reason through why it is only a false statement when P occurs, but Q does not follow. So we would say, if Maria learns discrete mathematics, let's abbreviate that, then Maria will find a good job. Okay, so if, say, Maria doesn't learn discrete math, does that mean she won't get a good job? Probably not. So the only time, if I said, Maria, if you learn discrete mathematics, then you will find a good job. That doesn't mean the only situation that she'll find a good job is by learning that discrete mathematics, but she would call me out as a liar if I said, if you learn discrete mathematics, then you'll find a good job. And suppose she learns discrete mathematics, but she doesn't get a good job, then you could again call me out as a liar. So the only time this statement would be false would be when Maria learns discrete math, but the consequence is not that she finds a good job. Let's look at another example. What is the value of the symbol x after the statement, if 2 plus 2 equals 4, then x equals x plus 1, if x equals 0 before this statement is encountered? Okay, so there's our if-then statement. So if 2 plus 2 equals 4, then x is going to be assigned the value of x plus 1. Well, the statement 2 plus 2 equals 4 is always a true statement, right? 2 plus 2 equals 4 is always true. So this is always true. And we're saying that an if-then statement, when the condition happens, the conclusion must follow. Therefore, x is going to be assigned the value of x plus 1. So x will now equal 1 coming out of this if-then statement. While not always true, we also have something called the converse of a statement. The converse of a statement is basically just switching the condition and the conclusion. And I've been using that language. This is called the condition, and this is called the conclusion. So if you switch the condition and the conclusion, you get the converse of that statement. If I am in Paris, then I am in France. Well, the first thing I want to do is I want to identify P and Q. So there's P, I am in Paris, I am in France is the statement Q. And so to write the statement Q then P, I would want to say, okay, well, if I am in France, then I am in Paris, and clearly that's not always going to be a true statement. I could be in France, but I could be in a different state, a city, so this is going to be a false statement right here. I could be in other places within France. I don't have to be in Paris. But if I am in France, then we know that Paris, if I don't know what the shape of Paris, here there's a shape of France, let's just say for fun. And Paris is in here. Therefore, if you are in Paris, you know you're in France, but the opposite or the converse does not necessarily hold true.